All right, let's continue our journey in section 6.3, which is logarithms and logarithmic functions. And today, we're going to continue on simplifying different expressions and also taking a look at these logarithmic function graphs here. You're going to want maybe some more paper for those of you that are doing work in the student journal, because you're not going to have enough space. And I want to add some extra examples here as we take a look at things. As we start off with number 13, we have base of 13 raised to the log base 13 of 6. Now, this is a little weird, but one of the things that the rules that we have here is this. If this log base, or the base and the log base right there, happen to equal or are the same, then what that ends up doing is that it's like the inverse, and that gets rid of the log, and this ends up equaling to be 6 right here. All right, so you want to, one of the things you want to look out for is if the log base matches the base of the exponent, right? Or if the base happens to be the same thing as the exponential log, the log that happens to be in the exponent itself. All right, next up, let's take a look at number 14. On number 14, we have ln times e raised to the x to the third power. And one of the things that I had mentioned earlier on right here is that, or maybe I did or maybe I didn't, but ln and e, they are inverses of each other. All right, so what ends up happening right here, if you, the ln and the e, since they're inverses of each other, they eliminate, and now we have our answer, which is x to the third power. Next up, let me go ahead and give you a few other examples here to kind of solidify your understanding of this. First example I have, I'll just go ahead and put it like extra. Some extra practice here. The first one, I've got, we'll have 8 as the base, and then I'll have to the log base 8 of x. Right. So once again, taking a look similar to that of number 13, the base happens to be the same as the base in the exponential log. So this ends up equaling x. Let's have another example. This time I have log base 7 of 7 is equal to negative 3x. Well, something a little different here. This time the log base is the same as what it is of. When that's the case, my answer is going to be the exponent, which is going to be negative 3x. In the third example, or extra example right here, I have now log, let's have base of 2, and then 64 to the x power. All right, things are going to get a little more complicated right here. Remember, in order for me to bring that exponent down or solve for x, remember, if I look at number 2, my log base has to be equal to what it is of. Right here, my log base of 2 does not equal 2 to the x power. It's 64 to the x power. this is where you got to get creative and think, all right, that's 64. Can I rewrite that where it has a base of 2? And I can't. I can go ahead and rewrite this where it's log base 2. And then 2 right here, if I raise that to the 6th power, that equals 64. And then right here, I still do have my x. That does not disappear. And that'll be up at the exponent. So how about now? What do? Well, because the base happens to be the same as what it is of, now I take when I raise the power to power, I multiply. And so right here, all of this now simplifies down to 6x. Your answer. Isn't it so neat how all this stuff works out? It's pretty crazy, pretty wild. A lot of rules here, though. Huh? Next up, number 4. I got my 4th example right here. So let's say this time I have e raised to the ln power times 20. Well, just like number 14, when I have ln times e, those are inverses right here. When I have e as my base raised to the ln power, that leads me to my exponent, or my answer, which happens to equal 20. All right, so we have 4 extra examples right here to help you out and get you through this. And that should kind of get you through most of the different scenarios that you'll see in your homework. Let's go ahead and move on now. Let's take a look at number 15. We want to find the inverse of the function. If you remember before, in order to find the inverse of functions, you had to switch x and y and then solve for y again. And so that right there will be the same thing that we will do right here. Okay, we will execute the same thing. So let's start off. Let me go ahead and switch x and y. I have x is equal to 15y to the y power plus 10. And I want to go ahead now and solve things out. Let's start off. We'll move the 10 over to the other side, so we'll have to subtract 10 to both sides. And so we have x minus 10 is equal to 15 to the y power. All right, so now we got to figure out, well, how am I going to bring that y down? That's where we take a look at some of the examples that we just looked at, some of the extra problems, looking maybe at number 13. How is it that, what can I do to both sides so that I no longer have that 15 or y as an exponent? Remember, if the log base is the same as what it is of, then that'll bring that exponent right down. So here's what I'm going to do to both sides. I'm going to go ahead and multiply both sides by log base 15. Let's see if I can fit that in. We have log base 15. So now that I'm here, on the right-hand side, we'll just say that that cancels out. And I'm now left with y is equal to log base 15 x minus 10. And now you have your inverse. Let me throw in another example right here, a little bonus example for you guys. Let's go ahead. This time we've got y is equal to 4 to the x power. and we want to find the inverse. So we'll start off. We'll go ahead and switch x and y. So x is now equal to 4 to the y power. And once again, kind of reinforcing what we just did on number 15. In order to bring that y down, I'm going to go ahead and have to multiply both sides by whatever the log base is to make it match up. And so I'll multiply both sides with log base 4. And so now I have log base 4 of x is equal to y. A little bonus example for you guys right there. I know how you guys always want more, right? Always want more. Next up, number 16. So let's go ahead and we'll switch x and y out right here. So x is now equal to ln 2y minus 8. So let's now, we'll move that 8 over by adding it to both sides. And so we have x plus 8 is equal to ln times 2y. Okay, so we have an ln, but we don't have y by itself because that ln is in front. Let's take a look at maybe some of the examples we have right here. What can we do? What can you do? Is there any of the examples that we just had that might help you along the way right here? How about if you take a look at that last example that we did of the extra ones? When I had e as the base, that got rid of the ln. So what I'm going to go ahead and do right here is I want to put e as the base for both sides. Okay, so I put it down below to show that that is now my base. And so let me rewrite this. On the left-hand side, e is the base. We have x plus 8 power, and that is now equal to 2y. Fantastic. All right, we have one last step. We'll divide both sides by 2. Okay, so we'll divide both sides by 2, and y is equal to e raised to x plus 8 power divided by 2 right there. All right, so we've taken a look at several types of inverse problems. Let's see. Let me give you another bonus one right here. Erase this that we have on the side, and let me give you another extra one. We have in this example y is equal to ln, and then we have x times x minus 5. So once those same rules apply, we're going to find the inverse. I'll switch x and y. And let's get rid of that ln. So we're going to go ahead and include now a base of e to both sides of the problem. And so now on the left, it's e to the x power. The e raised to the ln, that gets rid of that ln and the e. And now we can go ahead and safely bring down the y minus 5. I got to get y by itself for the last thing. And we're going to now add 5 to both sides. So this time it's e to the x power, but it's not going to be in the exponent. I'm just going to go ahead and put plus 5 next to it and set that equal to y. And now we have our inverse. the last thing for us to look at, I'll go back to our notes right here where we're talking about parent graphs of logarithmic functions. Okay, that right there is on page 167 of the student journal. And so I think one of the big important things to realize here is this. When we're looking at the logarithms and exponential functions, remember, they are inverses of each other. Okay, so let me highlight that right here. They're inverse functions. Okay, logarithms, exponential functions, inverses. And so right here, remember, when it comes to inverses, they reflect across a line. That line happens to be the dotted line that's there. And remember, that dotted line is equal to y is equal to x. That is the equation of that function. So you can see right here that up above the dotted line, they've got the function of y is equal to b raised to the x power. Down below is the inverse of that, which happens to be y is equal to log base b of x. Cool, right? They reflect, remember, if I were to fold the function across that line of y is equal to x, then it would overlap each other. There are some other things to note. We have some vertical asymptotes. Okay, we do have some asymptotes here. Right here with the log base b of x, this green part, this section right here that I'm going to go ahead and keep writing, there's one of your asymptotes. It just starts dropping straight down. So the vertical asymptote right there is y is equal to x. Or sorry, x is equal to 0. All right, so there is your vertical asymptote, the y-axis. So therefore, the domain right there for this happens to be, they're saying that the domain is when x is greater than 0. Now, how about for the exponential function? We have right there a horizontal asymptote, right? Because if you look down right here at this part, it doesn't cross the x-axis. So my domain is all real numbers. However, the range right here, we gotta realize is the range is x, or sorry, it's y is greater than 0. And there's that part right there. And there you go. They show you another example of functions, the log of log base b of x, and then the two inverses of those right there. Okay. So now that we've got that down, let's go ahead and graph our own and take a look at number 17. So the question says, let's graph the functions and then determine the asymptote of the function. All right, so if I wanted to graph the function, we've got for a logarithmic function, it doesn't help us because we don't know we can't really graph a log unless you use a graphing calculator. So let's just say, okay, you don't have a graphing calculator and we're going to try to solve this out. Well, what can I do? I've got to figure out, well, what are some values? What are my values of x and what are my values of y? To start off right here, let's go ahead. What you're going to have to do is you take x and y, and so you find the inverse of each other. So let's go ahead, and we now have x is equal to log base 2 y plus 1. All right. And now the reason why you can't use just your calculator is because, remember, in your calculator, it assumes that your log base is 10, but my log base is 2. And so that is another reason why we've got to find the inverse function first, which is what we're going to do right now. And so let's go ahead. In order for me to do that, my log base of 2, what I want to do is go ahead and put 2 as the base on both sides. So what that gives me is 2 to the x power is equal to, this all cancels out, and then I have y plus 1. And then from there, let's go ahead and subtract 1 to both sides. So I have 2 to the x power minus 1 is equal to y. All right, so now we have figured out, we have a usable equation for us to create our table. Okay, so now let's go ahead and create a table. And so I've got x, I've got y. Let's go ahead now, knowing the function right here where it's 2 to the x power and then minus 1, that minus 1 talks about a vertical shift. So we can go ahead and use -2, -1, 0, 1, and 2 because it's not shifting horizontally. And then from here, let's go ahead and you can start plugging in numbers, or plug those things into your equation and figure out what y is. All right, so we have for x and for y, when x is -2, y is -0.75. When it's -1, we have -0.5. When it's 0, we have 0. When x is 1, we have 1. And when x is 2, we end up with 3. All right, so those are all of our functions. But remember, these points right here is of y is equal to 2 to the x power minus 1. Those are not the points of log base 2 of x plus 1. So hopefully, instead of doing a bunch more work, okay, what can we do? Remember, the rule right here is this. For the inverse, use the table and switch x and y. So if I switch x and y, those will be the points of log base 2 of x plus 1. So the points for log base 2x plus 1 will actually end up being, we have -0.75, -2, -1, -0.5, 0, 0, 1, 1, 3, 2. And those right there will be your actual numbers and functions. All right. So let's see what happens. Let's put it all together. Let's take a look over here on Desmos. All right, so we have the original function, which is what we're trying to find. And if I go ahead and I plug this in and I already have it there, I'm going to go ahead and turn on that function, and it looks like this. Beautiful. All right, so these points that we have, if I look at the table, they match up with what I had in blue, right? 0, 0, 1, 1. I didn't have 2, but then at 3, it's at 2. But then guess what? There's a few other things that show up there. It says that, we got a -1. We're at undefined, -2, undefined. Well, why is that? Okay. Well, first of all, if you look at the function right here, take a look at it carefully. What happens as we start going downwards right here at -1? It gets very close to it, but never touches. What does that mean? We have an asymptote. Therefore, right here at -2, no good. At -1, no good. Because it reaches that asymptote, we have a vertical asymptote at -1. So that would be one of the asymptotes of our function. The thing here is this: if we plot and show the other graph that we first found, the inverse, you'll see it in blue of what y is equal to 2x to the x power -1 happens to look like. And there you go. If I look carefully, though, these two functions are actually reflections of one another. Are they not? They are, because remember, if we were to draw a line of y is equal to x, it'll actually go through here at 0, 0. It'll go through right there at 1, 1. And then it'll be this diagonal line that goes through those 2 points. And so you'll have yourself a reflection right there. And we have now graphed these two functions. All right. And there you go. You can now graph logarithms. All right. So you hopefully become a master at logarithms at this point. And we have now finished 6.3.